We're going to continue discussing exponents and roots. And just as a quick review from the previous video, we sort of left off with the negative exponents and doing some of these questions. All right, so we just want to understand, first of all, what a rational power is. And so basically what it is if you have a fraction, that's what a rational is, all right, then the denominator of the fraction becomes the index of a radical, okay? And the numerator becomes a power on the base inside the radical. So the denominator of the fraction becomes the index of the radical, and the numerator then is either, you can write it on the outside of the whole thing, or you can write it inside with the base. They're the same thing. Okay, so this just sort of shows you again, but we'll do a few examples just so you can see. So x to the 2/3, the index becomes the denominator, so it's the cube root, and then the numerator becomes a power, okay? 3x to the 4/5, we write that as the 5th root of 3x to the 4th. You could write it like this, all right? So you could write it in here like so, or you can write it like that, okay? Either way. What happens with this one is negative, so what you're going to end up with is x is going to get flipped and make it 1 over x to the 1/2. And then if you have a 1/2, you have the square root, so it becomes the square root of 1 over x. But then the square root of 1 is just 1, so that's why we can write it as 1 over root x. Okay. If you're going the other way, which these are, it's just whatever the numerator is this guy, whatever the power is on the base inside the radical, and the denominator is the index again, so it becomes 5/3 or 9 over 7. Okay. And if you look at this, you have 2 to the 1/7 because it's 2 times x to the 9. Okay, the whole thing is raised to the 1/7 if you write it as a power first, and then it gets put in. Okay, so it's 2 to the 1/7 and then x to the 9/7. So that's why it's not, because the 2 is not raised to the 9th power essentially. Whereas here, the whole thing is raised to the 5th power. So that means it's 6x to the 5 over 2. In other words, the 6 is included. All right. So that's the idea of rational powers. Then what we end up with is an application of exponentials that involves rational powers. And it is the concept of exponential growth and decay. All right. So the way that we sort of look at this is A is the initial amount that you're given, and then you're going to be told that it's going to do something. It's either going to double, or it's going to have a half-life maybe, or you might end up with something where it's interest. So you might say something is going to give you 10% interest or something like that. That becomes the base of an exponential, where t is the total amount of time that goes by, and p is the period of growth or decay. In other words, it's like how long does it take to do whatever the base is doing. So if it's double, how long does it take to double? If it's half, how long does it take to go halfway? All right, or become half of what it was. So we're going to use that to solve some exponential equations. So here's an example. It says a biologist makes a sample count of bacteria in a culture and finds that it doubles every 3 hours. The estimated count over 6 hours was 10,000. What was the initial size? So what we're looking at in terms of this solution is y is 10,000, okay, because that's the sort of final amount. A is what we're looking for. We want the initial amount. The base is 2 because it's going to double. The time, it says, was 6 hours, the total time, and the doubling time, which is our p value, is 3 hours. So we're going to go 10,000 is equal to a on the 2 raised to the 6 over 3. So that gives me 10,000 is a times 2 squared, which means that's 10,000 is 4a. 2 squared is 4, and that means that a is 2,500. And then it says for part B, what will the count be after 1 day? Well, 1 day is 24 hours. So you go y is equal to the initial amount, which is 2,500, on the 2 to the 24 divided by 3. Okay, so that's 2,500 times 2 to the 8th power. And that, if you do it on your calculator, comes out to 64 or 640,000. Okay, so that's my answer for that one. So that's how we use exponential growth or decay, that formula, in a situation where we have exponential growth or decay, where something is doubling or half-life or something like that. It's growing. Okay, so here are some more examples, and I know these are hard to see. We're not going to go through all of them, but I just want to point out this one. It says the population of a nest of ants n is given by this formula: 500 on a 1.12 to the n. That's an n. Okay, where n is the number of weeks. So to get the answer for this, for 10 weeks, we will go 500 times 1.12 to the 10th power. For 20 weeks, we would do 500 times 1.12 to the 20th power. Okay. Again, this one's given us a formula. It says this is, again, it's hard to see, but it's 20 times 1.007 raised to the t. So it says, what's the original weight of the bacteria? The original weight is 20. Okay. And then it says find the weight of the bacteria after 21 hours. So you would go 20 times 1.007 to the 21st power. And I'll leave you to do that on your calculator. Okay. Then the next question is talking about rabbits. We'll skip that one. I think you can probably see. Actually, let's not, just because it asks something a little bit differently. It says it doubles at regular intervals. So it says you bring 100 rabbits, so that's your initial amount. It's doubling, so your base is 2. And it says 2 years later, so your total time is 2, and you're looking for P. And there it says there were 6,400 rabbits on that island. So you would get 64 is 2 to the 2 over P, and then you'd have to recognize that 64 is 2 to the 6th power. So that means you get this. And once the bases are the same, the exponents have to be. So that means P, 2 over P, sorry, is equal to 6, which means that P is 2 divided by 6, or 1/3. So they would double every third of a year, okay, because the time unit's in years. So a third of a year would be 4 months. So we could say a third of a year, or we could say 4 months. And then it says, what would it be in an additional year? So now we would go back and we would say, okay, what's y then if we have 100 times 2 raised to the 3 years over 1/3? And you get 100 times 2 raised to the 3 divided by 1/3. I know you can't see that very well, so let me just write it here. It's 3 divided by 1/3. That's the same thing as going 3 times 3 over 1, right? Because you invert and multiply, so you end up with 9. So it's 100 times 2 to the 9. And then again, you can do that on your calculator. Okay? I'm going to do one of these because it's a half-life question. So let's just do number 5. It says the half-life of palladium 100 is 4 days. After 16 days, a sample of palladium 100 has been recorded of a mass of 0.75 grams. So we know we have 0.75 grams at the end of it. We have A, then the base becomes 1/2, right? Because it's half-life. And it says the half-life is 4 days, so that's P, and it's been 16. So you get 0.75 is equal to A onto 1/2 to the 4th power. So that means 0.75 is equal to A times 1 over 2 to the 4th, and 2 to the 4th is 16. So that means that 16 times 0.75 is my A, and that's 3/4, so you end up with 12. So A is 12. Okay, so there was initially 12 grams. And then it says, what's the mass after 2 days? So again, you would go then 12, you go y equals, but then 12 is my initial amount. I have 1/2, and it would be 2 over 4. Okay, and then again, you can get that to be 12 to 1/2 to the 1/2, and then you would just have to solve that on your calculator. So that's the idea behind exponential growth decay kind of questions, okay? And you can look at these solutions. If you look back at these questions, we did a few of them. I didn't go all the way through them, so you can figure out where you went wrong or where you went right. So we've got a third of a year. I did that one, but the rest of them you can sort of find out on your own and see if you did them right. So we'll leave it at that, but that's an example of exponential growth and decay.